Today in this class, let me introduce to a problem, integer programming problem, using the method branch and bound technique. That is, we are going to use a different technique to solve a given integer programming problem. In my last class, I explained to you what is the meaning of integer programming problem and also gave a brief idea of how to solve a integer programming problem using two methods. One was the Grammarian constraint, that is the cutting plane method, which was the technique was used to solve a problem, and it was done in my last video. And in today's video, I have again taken up an integer programming problem, but the method of solving is using the technique branch and bound. And branch and bound is a technique which I can use graphical method for this branch and bound method technique, and also the simplex method. But when you use the simplex method, you have to prepare the iterations and you will have to create additional problems, and for the additional problems you have to use the simplex method, and I am 100% sure that it will be a very long and a laborious process, and there is every chance that the student might commit mistakes in their calculation. So, and also sometimes it is frustrating in the sense that too much of calculation will make you disgust with the problem. So in order to avoid that, my suggestion to the students is that better use this graphical method technique. But when you use this graphical method technique, you have to be very careful and meticulously doing the problem and finding out the area in which the solution lies, and when you cut down the areas, you have to be very careful where your solution lies. Accordingly, you should employ more carefulness in order to decide the region and also the drawing the diagram, and all these things are very, very important. But comparatively speaking, this will be better than the other one, because the other one involves lot of cumbersome calculations. So better you avoid that. But still, if you practice that, it is good. But my suggestion to my students is better practice this, and it is also a method of doing it, so you can practice that also. But today I am going to take this class. In this class I am going to teach you the method of the graphical method, and that is branch and bound technique. While I will tell you what is the real meaning of that branch and bound technique, what is the meaning of bound, branch and everything, I will explain to you while I proceed with the problem. Okay, now here understand that another thing that I want to make one point clear is that this method, graphical method, can be employed to find the integer solution only because we have got two variables. By chance you have got three variables and you are supposed to find the integer solution, this method cannot be applied. You have to employ only a simplex method, because graphical method can be used only when there are two decision variables. So this is a very simple and obvious reason that we cannot use the graphical method if the number of decision variables are more than two. Okay, now with this small introduction, let me come take up the problem. Now what is given here, I require a lot of space here, that is why I have written my problem here. Now you see that, now what is the main principle of, first of all, as we used to do in simplex method, use the simplex method, ordinary simplex method, to find the solution immaterial of whether we are getting integer solution or not. We are not bothered about that. Simply solve it. Simply use the simplex method to get the solution for the linear programming problem. Here, simply draw the graph and get the solution. That's all. Try to get the maximum solution for this particular problem using graphical method, immaterial, without minding whether you are getting integer solution or the rational solution. By the by, try to understand what is a rational solution, in the sense rational number. Any number of the form p by q with q not equal to 0. Here I will take that p and q belong to your natural, means a fraction. In a simple sense, what is that you must understand by a rational number is that it is a fraction. So your decision variables cannot be fractions. Okay. Now, and another thing, that just know that some of the, for example, if you are a student of operations research or a resources management techniques, learning these subjects, you would have come across transportation problem, in which you will find that you will that is assignment problem. You would have even transportation problem. You will come across the allocations. You will come across a term called allocations for a destination from a source. From a source to destination, yes, an allocation of goods will be there, and that allocation of goods will be a integer. It is not a fraction. Another example is that your assignment problem. Assignment problem is the one which is the minimization problem always. That means you are, in the sense, normally it is a minimization. It can be also maximization. What happens in that problem is that you assign a work to a person, or you assign a job to a machinery. When you assign, you take the value as 1. When you don't assign, you call it as 0. That means 0 and 1 are integer. Therefore, your assignment problem is the integer programming problem. Your transportation problem is the integer programming problem. These some of the examples, even sequencing problem. Likewise, see, we have got a mixed integer programming problem. Means suppose you are a manufacturer of TVs or say chairs and tables. You will find that the number of tables, chairs or TVs or cannot be a fraction. They have to be whole numbers. They have to be integers. But in the case of rupees, that is, you pay for the cost of the articles, the cost of the things, need not be an integer. They can also be fractions. So you see that your cost of products can be fractions, but the number of products cannot be fractions. They have to be integers. So in this case, it's a mixed integer programming problem. Can you understand? So these are the things that you must know, because then only in your examination, if they ask you, you will be able to write that. So these are some introductory ideas that I am giving before going into the problem. Okay. Now, coming to this. So what is that here? Let me draw the graph without giving any importance for integer. Now what is that you will do? So you take this equation, say I write everything here calculation because I require a space here. So you take this equation now. What is this equation? 2x1 plus 2x2 is less than or equal to 7 means always know that when you are drawing an inequation, first of all you draw the equation of the line. What is it? When you are going to draw an inequation in a graph, first of all draw that equation of the line. Then decide from the given problem whether you want a region above the line or below the line, as the case may be. You are able to understand. Suppose if it is greater than or equal to, above the line. If it is less than or equal to, below the line. Like that it goes on. And it all depends on the equations given, inequations given. So you have to first necessarily draw the line of the equation, line of the inequation. So what is that here, inequation here? So this is. Now you take x1 is equal to 0. Take x1 is equal to 0. So x2 is equal to 7 by 2. I hope that you are able to understand. And you give x2 is equal to 0. So x1 is equal to what? You take x2 is equal to 0. x1 is equal to 7 by 2. See, I hope that these are all very simple working that I'm not writing. Otherwise, I will write fully what I don't mind write fully. See, what I mean here is that, first of all, I want 2 points. If you have more number of points, it will be easy and accuracy will be more. But even if you have 2 points, I can join them by a line and it gives a equation of a line. Okay, now in this case, this is the equation of the line. So in order to draw this line, I just I take x1 is equal to 0. See, I take x1 is equal to 0. So this is 0. So 2x2 is equal to 7. So x2 is equal to 7 by 2. This is 3.5. And likewise, you take x2 is equal to 0, you will get 7 by 2. So you see that I am able to I can draw the line because I have 2 points, 0 and 3.5 and 3.5 and 0. So I am totally determined of the points that are to be plotted on the graph to draw the line. What is that line? 2x1 plus 2x2 is equal to 7. Okay. Now the next two are very simple. Say this is equation 1. This is equation 1, this is equation 2, this is it. Now x1 is equal to 2 line. x1 is equal to 2 line is a line parallel to y-axis. And x2 is equal to 2 is a line parallel to x-axis. That I will draw and tell you how that is done. Okay, now see, let us take this and know that I want only the first quadrant here. I want only the first quadrant here. I don't want anywhere. I will not go here or here or here because I know that my values of x1 and x2 are greater than or equal to 0. They are not at all negative. Okay, now let me confine only to this. So this is your 0, 0. Now draw this. See, 1, take equal spacing 2, 3 and 4. See, this is 1, 2, 3, 4. Same length I will take here. So this is 1, 2, 3, 4. So this is 1, 2, 3, 4. Now for this line you want 0 and 7 by 2. 7 by 2 is what? 3.5. So your 3.5 will lie somewhere here. And for this it is 3.5 will be somewhere here. Now you draw the line like this. So this is a line. So what is that I have done here? I have not done anything big here. I have simply drawn this line. That's all. Now, as I told you in the beginning of the class itself, that if you are going to use a graphical method, then drawing a graph for the problem is it has to be in the way that first of all draw the equation of the line. Then decide according to the problem whether it is above the line or below the line, if it is less than or equal to or greater than or equal to. Okay, now coming to this, what is this? I have drawn the line. Less than or equal to means what is that? You know what is the meaning of that? Say you vary the values of x1 and x2 in any way you like and substitute them here in this x1 and x2. Add them. Its value must always be less than or equal to 7. Are you able to understand? It can go up to 7, it cannot exceed 7. That means here you see that your line, all the points below the line, So you see that below the line means you can take all the values in this triangle. So I will put this triangle here. It is 0, O, A and this is B. So OAB is a triangle in which you get all the points. Here every point is a coordinate. Coordinate means x1, x2 coordinate. So you see that you take all the points on the line or below the line. Don't here or here go. Don't go here because you must be only in the first quadrant. So you see that OAB is a triangle which contains all the points and all the points will satisfy this inequation. That means you take any point here and substitute in x1 x2, you will find that 2x1 plus 2x2 is always less than or at maximum equal to 7. Therefore, my region, my domain where I can get the points to satisfy this equation is 2x1 plus 2x2 is equal to is the points lying in the region OAB. So if it is the first one, because you have to shade. Now since this is my first region, let me not shade. Now, so if it is required, you shade that, okay? But I don't shade, I take this white color itself as my shade and leave it like that, okay? Then, let me come to this. See what is, so this is drawn, so this is drawn. I don't shade here. Mind that we have to shade this portion. OAB triangle has to be shaded. My understanding is that in all this integer programming problem, better don't shade. If you're going to shade, you shade, more shade will come and you will find difficult to identify because you're going to create number of problems. Sub-problems you're going to create. When you create sub-problems, all the shade will give you confusion. So better it is you don't shade. Try to identify in your mind itself and keep it register in your mind itself where you are. Okay, it will be better in that way. If you are going to shade, it is bound to create some confusion. So don't do that. My advice. Okay. Now coming to this. So you see that this is what you. So this is over. Come to this. X1 is equal to. First draw the line x1 is equal to 2. Now where is x1? X1 is on this one. And this is x2. X1 is on this and go up to x1 is equal to 2 and draw a line. I told you, draw a line parallel to y-axis. So what is that you will do? That means, what is the meaning of this? Where I have not drawn a straight line, right? This is a line. This is x1 is equal to 2. That means wherever you are on this line, you are at a distance of x1 is equal to 2. That is the meaning of that. Keep that in your mind. So wherever you are on this line, your x1 is equal to 2 only. It cannot be more than that. Okay. So this is what I. Then now what is that? X1 is less than or equal to 2. What is the meaning of that? You have to shade that region which will contain points which will be always less than 2. X1 is equal to 2 means less than 2. What does it mean? Within this space 0 to 2, you will get all the points which will be less than 2. This is x1 is equal to 2. So all the points less than 2. So this is the, where is your region now? So the region is, now I will put here O. See previously OAB. Now you see that I will write here O A dash and this B dash. That means what? O A dash B dash and B. Now your area has been reduced. That means what? Previously your area was OAB and now your region is, you have drawn this A dash B dash and this line, that your area has been reduced. That is O A dash B dash and B. That is your new area. What is that new area? Because there only you will get points. You get points which can satisfy this equation number 1 and also equation number 2. So what is that meaning of that? So when you're drawing the first constraint, it will constrain, the region will contain points satisfying only that inequation. But if you're going to draw the additional another constraint, it will reduce the area, and now the reduced portion or the overlapping portion of the portion caused by the first inequality and caused by the second inequality, they will overlap. For example, if I shade here, suppose I give a shade here. I give a shade means you see that this white portion and the shaded portion will overlap only in O, A dash, B dash and B. They will overlap only in that region. That means that region will contain points which can satisfy the inequation 1 and also inequation 2. And remember that you can nowhere you can go. You are totally confined only to O, A dash, B dash and B. So this is the area now as per the two given inequations. Now my area has been totally determined. Now let me draw the other one. What is that? You have to draw the other one. What is that? x2 is equal to 2. Now what is x2 is equal to 2? Your x2 axis is here, your 2 is here. As I told you, draw a line parallel to x axis. So what is that you will do? So x2 is equal to 2. Now x2 is equal to 2 is a line. Now this line is drawn, but as per this inequation you have to collect all, you have to consider only those points below the line, those points below the line which can satisfy this particular inequation. Okay, now that means what? You can draw all the points down below. Here you see that you will draw all the points down below, but already you have determined a region where the points can satisfy these two inequations. Can you understand? That means you are getting, let me call this as your B dash. This is B dash, means I will call this as my C and I will call this as my C dash. Now you see that now previously it was OAB. Now after then I told you that OA dash, B dash and B. It was reduced. Now that you have drawn another line like this, your region is, that means what? You are getting O, so I will draw here this one, this one, this one and this one. Can you see this? Now O, I'll write here O, A dash, B dash, C dash, C. This is a polyhedron which contains, that means what? Below the line, and this is left of the line, and in the triangle below this, and they will comprise a common area. I'll repeat this. First you got OAB as your region which contain points which can satisfy this inequation only. After then I drew the line x1 is equal to 2 and all the points to the left of it must be considered to satisfy this equation. But simultaneously you find that it cuts down a portion, cuts down the portion OA dash B dash B which contain points which can satisfy this equation and this equation. After then I drew the line x2 is equal to 2 and I found the points below to satisfy this inequation, but incidentally I find that the points, that is I get a region, common region, that is O, A dash, B dash, C dash, C, which contain points which can satisfy the inequation 1, inequation 2 and inequation 3. And these are the only three inequations given, and these three inequations bound an area, and that area is nothing but O, A dash, B dash, C dash and C, which contain points which satisfy all the three inequations. Hence, your solution for the problem is nowhere except in this region. Are you clear with this? So you need not go and search for a solution anywhere else. Your solution lies only in O, A dash, B dash, C dash and C. So this is how. So therefore this is called, see I have not drawn any shade, I have not shaded anywhere. But if you shade, you will get the overlapping of three shades that you are given. If you are giving the shades, there will be three shades, and the three shades will overlap only in this portion O, A dash, B dash, C dash and C, which is the solution region, and this region is called the feasible region. Feasible, I will write here as feasible. It's like this. feasible region. So this is called the feasible region. Why it is called a feasible region? Because it contains the area, it contains all the points which can satisfy all the inequations. That is the meaning of saying that it is a feasible region. Now you have to find, now what is your B dash? So your B dash. Now this B dash is the intersection of the line. See, what is your B dash? B dash is the intersection of the line 2x1 plus the 2x2 is equal to 7 and x1 is equal to 2. So you see that 2x1 plus 2x2 is equal to 7 and x2 is equal to x1. So this is x1 is equal to 2 and this line is what? It is 2x1 plus 2x2 is equal to 7. So when you solve this, you will get B dash. What is your B dash now? Put x1 is equal to 2. So this will be 4. So you see that when it goes to the right hand side, 3. So it is 3.5. So you will get x2 is equal to 3 by 2. So what is that you get here? So you put x1 is equal to 2 because this is x1 is equal to 2 is a line. I am going to solve this equation and this equation to get the point of intersection. So you get x1 is equal to 2. So this is 4, this is 3, 3 by 2. So what is this point? This point is 2, 3 by 2. Now this is 3 by 2. And now since I have done this, I will go for the next one. So you see that what is this point now? What is this point? So this is see, yeah. Now what is this point now? C dash. What is your C dash now? Your C dash is what? Solve this 2x1 plus 2x2 is equal to 7 and this x2. That means 2x1 x1, this is x1 is equal to x. This is x1. So what is this point? So 2x1 plus 2x2 is equal to 7. Take it, this x2 is equal to 2. So you will get x1 is equal to 3 by 2. So what is your C dash? C dash is also so C dash is your 3 by 2, 2. See. So your C dash is 3 by 2, 2 and this is your C is 0, 2 and you get this to be, you know, this. So this O, this A dash is 2, 0. So O, 0, 0, A dash, B dash, C dash and C. And what is this? A dash is 2, 0, B dash is 2, 3 by 2, C dash is 3 by 2, 2 and C is 0, 2. Now these 4 points form a polyhedron and that polyhedron is called the feasible region and it is a convex region. It is called a convex region. We call it as a convex region because if you take any 2 points anywhere within that region and join by a line, it will wholly lie in the region. That is the definition of a convex region. A convex region is a region in which a randomly chosen 2 points, if joined, the line will lie in the same region. That is the definition of a convex region. So you see that this will be a convex region and every point is a solution. Understand that every point in that region is a solution, but all points cannot be maximum. All points cannot be maximum. There are cases where every point is maximum. That can happen also, but and every point can be maximum. Unbounded solution can be there, infinite number of solutions can be there, unbounded solution can be there and no solutions possible. So you see that there are cases here in the problems where unbounded solution can be there, infinite number of solutions can be there and no solutions possible. So you see that here in this particular, so there is every possibility that you can have unbounded solution or infinite number of solutions like that. And here in this particular region, we have got a region, but in this particular region, I should say that you do not have such complications. It is not there. And another thing that you must know is whether it is going to be a maximum or minimum maximization or a minimization problem. When you draw the graph, in the graph the maximum or minimum will occur only at the vertices of the polyhedron. See, max or minimum, I'll write here, max or min will occur only on the at the, see, max or min occur at vertices of the polyhedron, feasible region. So you see that whether it is going to be maximum or minimum, your this in this part. So here in this polyhedron, where will you get the maximum? Either at 0 or at A dash or at B dash or at C dash or at C. So these are the 4 points where you will get the maximum. Now we will find out where this where you will get the maximum. How you should do that? Say, I'll rub off all this. I'll rub off all this here. So you see that here max of Z is equal to, see here, I will write here, vertices max of Z, it is 3x1 plus 2x2, 0, 0. First you take 0, 0. When you put 0, 0, obvious, it is very clear that it is 0. Then you go for what? A dash, 2, 0. When you put 2, 0, it is 6. Then you come to B dash. It is 2, 3 by 2. It is 2, 3 by 2 means what? It is 6. 2 into 3 is 6. And this is 3, that is equal to 9. And you come to C dash. C dash is 3 by 2, 2. 3 by 2 is what? It is 9 by 2. Plus 2 into 2 is 4. This is 4.5. So it is 8.5. And your C, what is your C? It is 0, 2. And 0, 2 means what? It is 0 and it is 4. Now which is your maximum here? Yes. Now we have got the, so this is a graphical method. Understand that I have not done any video on graphical methods, but this has given me an opportunity to teach you well on how that graphical method is done. So you see, this is how we do the graphical method. So I have taught elaborately what is the meaning of the graphical method and how it should be done. And when situation comes or when occasion comes, I'll tell you more on this. Now another point I want to make here. In one of my videos while doing my simplex method, I told that the iteration means repetition of the process. Iteration means repeating a process again and again, and that process has to be repeated under certain conditions only, unless and until you are getting the maximum solution, or you will not get a solution. This is what I said in my earlier videos also. Here again I told at that particular juncture that how it is compared with the graphical solution. Why that? What is the iteration and what is how should we understand in problem doing using graphical method? I'll tell you. Iteration means repeat the process again and again under certain conditions, unless you are getting the final solution, maximum or minimum. Here you see that here this is my first iteration, like 0 solution. 0 solution is not a solution for me. I want a good solution. So here, and another thing that you must know is that by a solution, I don't mean this as my solution. That is not my solution. My solution is finding the values of the decision variables. So I make it very clear that finding the values of the decision variables is called the finding the solution to the problem. So if I ask you to find the solution to your linear programming problem, means not that you are finding the objective value. Objective value is maximization or minimization, but my idea is to get the solution, means find the value of x1 and x2 or x1, x2, x3 or whatsoever be the decision variables. So you see that that's what I am going to do. So here your 0, 2 is a solution, 3 by 2, 2 is a solution, 2, 3 by 2 is a solution, 2, 0 is a solution, 0, 0 is a solution. Now after applying these values, we find whether it is maximum, whichever is maximum, which is going to give you the maximum. So you see that this is my first iteration 0. So I don't want that, because that, and you jump on to another one 6. It is not a big solution, and you go, let us suppose that you get next 8.5, that is also not a good solution, and you jump, and 4, you may get 4 as your solution, that is also not correct. But which is the maximum here? 9 is the maximum. That means what? You iterate, you jump from one vertex to another vertex till you reach that vertex which gives you the maximum or minimum. So in the iteration process, you give iteration or do the iteration again and again under certain conditions until you reach the final solution. So there the iteration, number of iterations matter. Here the vertices matter. Are you able to understand how this is done? So this is all about this. Now coming to the problem. So you see that this is our maximum. So that means what? I will concentrate only on B dash, because that is going to, so this is my 2 and 3 by 2 gives me the maximum, but that is as a linear programming problem using graphical method. I am getting the maximum solution for x1 is equal to 2 and x2 is equal to 3 by 2 and the maximum is 9. I am totally satisfied. But this is not the solution to the problem, because here it is being said that x1 and x2, and here you see that here I think I do not know, here you see that x1 x2 belong to integers. I told you that they are integers. X1 and x2 are what? Integers. Integers means I gave a lot of explanation that it can be 0 or it can be any positive natural number. So you see that this is, here you find that 2 is a integer, but 3 by 2 is not an integer. So that 3 by 2 has to be converted into an integer using, what is that? Branch and bound method. In my last video, I used the Gamorrean technique, Gamorrean constraint technique. It is a cutting plane method, but here in this particular case, I am going to use branch and bound method. So the maximum that I have got here is B dash 2 3 by 2, for which 9. So my best choice is B dash 2 3 by 2, and I will use that. I will use that particular maximal value and try to convert 3 by 2 into an integer. And know that another point I want to emphasize here is that you, after listening to my teaching, if you refer any book and do, you will understand better. You see that here this 3 by 2, it is 2.5. Why not we correct it below or above? Take it as 2.5 as 3 or 2.5 as 2, whatever it is. But you see that when you are going to manually correct the digits, that is correct the decimal places to integers, what will happen? The defect that you will come across is that if the optimal, that is the optimal solution may become very huge. It may change and give a better value. But know that these two coordinates, that is x1 value after x2 value, after changing it, will not satisfy any one of the constraints or any other more constraints. I will repeat that again. Why we don't change? Why we don't change this manually, in the sense that if it is 2.5, it is 1. Sorry, here it is 1.5. I don't take either 1. I can either take 1 or I can take 1.5 to 2. But if you are going to correct it in that way, you may get the solution 9 to be, it is not disturbed. Your maximum value will not be disturbed. But this 2 and the corrected value may not satisfy a constraint. If that is, understand that all the solutions that you are getting, they should satisfy all the constraints, and then only it will be called as a solution. Try to understand all these are very important. If you say that it is a solution, can be a solution only when it can satisfy all the given constraints. But if you correct it in the way, there may be a chance that your optimal solution may be high, very huge, but they may not satisfy at least one constraint. Even if one constraint is not satisfied, that is not a solution. Are you able to catch? And another defect is sometimes the optimality, all the constraints may be satisfied. The 2 points, the changed points, coordinate, and also the another point, if you apply it in the inequations, all the inequations will be satisfied, but your maximum value will be drastically affected. It will be very much affected, very, very badly affected. So in both the cases, it is not possible. That is why it is not possible for us to correct a decimal number to a higher value or a lower value. Are you able to understand? You have to go by that method, Gamurian constraint method, that is cutting plane method, or a branch and bound method. Then you correct it, you see that both your optimality will not be affected that much, and also all the constraints will remain satisfied. Are you able to understand? So these are all things that you must know. Now let us come to the problem here. So you see that this is what I am having. So you see that here afterwards, let me concentrate only on this b dash value, and using this b dash, I'll try to go for changing this 3 by 2 to an integer, and thereby get an integer solution, and that also gives the maximum value. Maximum value in the sense 9 may get reduced, but it may not be totally drastically reduced. Are you able to understand? It will not be very badly affected. It will not be very badly affected. So it may get affected, but it will not be drastically affected. To a mild effect, it may get mildly affected. So you see that. So those things these things you should have in your mind. So let me go for this b dash 2 3 by 2 and make all. That is, I follow that branch and bound method and see that the 3 by 2 is also corrected. I get an integer solution which also gives me the maximum possible for this particular problem. Okay, now let me start doing this. I may not require this, so let me rub off this. Now let me rub off this. So I have taught you that this is the one that I am doing, so this I will take. So here, see, that's why you see I am not shaded anything. I am going to create sub problems, and I am going to draw lines. If I am going to draw, if you had shaded, now drawing the lines will make you more confused. That's why I have not shaded anywhere. It will be normally on all these problems, there may not be any necessary for you to shade and do the problem. You just keep it in your mind and do. Okay, now try to understand that we are in OA dash, B dash, C dash, C. That's all. Now, what is that you are having now? B dash 2, 3 by 2. Now, which is here? See, x1 is equal to 2 and x2 is equal to 3 by 2, which is equal to 1.5. Now, what is this 1.5? 1.5 lies between 1 less than 1.5 less than 2. This is clear now. 1.5 lies between 1 and 2. Now what I am going to do, so x2 value is equal to 1.5 and this 1.5 lies between 1 and 2. Now I am going to create two sub problems. See, what is that sub problem here? See, sub problem 1. This is my original problem. This is my original problem. OP means original problem. Here, because for my understanding, nowhere you will find in books. It is, I say, original problem. This is your original problem. This is sub problem 1 means your original problem. Original problem means what? Maximum of this subject to this condition, and another condition I will write is x2 is less than or equal to 1, and subproblem 2 is original problem and x2 is greater than or equal to 2. Now you see that I am going to coin two different problems, two subproblems. What are the two subproblems that I am going to do? My purpose of creating two subproblems is that I will go and search. See, before that I will tell you. Here you see that x2 is lying between 1 and 2. So I will go for this. So I can draw a line here, x2 is equal to 1, and I will go for search. See, you will not get between 1 and 2. See, between 1 and 2. Between 1 and 2, there will not be any integer solution at all. Between 1 and 2, there will not be any integer solution. You should either go below 1 or go above 2, so that 2 and above or 1 and below to search for an integer solution. In between 1 and 2, because you will get only fractional values in between 1 and 2. So below 1 and above 2 I will go in search. That's why I have written here. You see that x2 is less than or equal to 1 means, it means that you are now creating a problem in such a way that below x2 is equal to 1, it may be 1 or below, and below 1 you will try to go for searching, you go in search of an integer solution. And if I say that x2 is greater than or equal to 2 means what? 2 and above. And 2 and above means what? It may be within that region. And always know that your search for an integer solution should be well within the domain of the feasible region. Okay, now coming to this, so you see that this is the original. So your problem O, A dash, B dash, C dash, C is your feasible region. You cannot search for an integer solution or anything for that matter beyond this, outside this region. Know that first. Okay, now let me draw this x2. Now x2 I have given. So what is that? This is your original problem. This is your original problem. I have put x2 is less than or equal to 1. That means now how will you draw the inequation? Draw x2 is equal to 1. Consider all the lines, all the points on the line and below the line. That means what? Your x2 is equal to my first subproblem. This is my first subproblem. So I draw the line. So x2 is equal to 1. Now you see that I have drawn the line x2 is equal to 1. Now what happened is that here when you are drawing, let me call this as your C double dash and call this, see this point, you see that? Now this point cuts and this is lying well within this feasible region O, A dash, B dash. So your point of intersection of the new line must be in the region of the feasible region. Now you see that you are drawing this line x2 is equal to 1 and it cuts somewhere here. Can you see this? So call this as your B double dash. So this B double dash is a point which is cutting the what? Intersecting the line A dash B dash line. That means x1 is equal to 2 line. Can you see this? So it is x1 is equal to 2 line, it intersects and it is well within that what? Feasible region. It is not going outside. Okay, now so you see that now what are the points that you get? Here it is 0 0, it is 2 0. Here what is this point? This is x1 is equal to 2 and this is x2 is equal to 1. So what is this point B dash? This point B dash is 2 1. Are you able to catch how I am doing this? This is x1 is equal to 2, so your coordinate is 2. This is x2 is equal to 1, so your coordinate is 1. So what is that B dash? B double dash is the point of intersection of the line x1 is equal to 2 and x2 is equal to 1, and that is well within the feasible region. So that point can be considered for, you can consider that for a point for finding the maximum. Are you able to understand? So you see that now we have got 4 points now. So here 0 0, already the 2 0 was there and it was discarded for the reason that it is not giving us the maximum. So don't bother about that. Now come to this point. Now you have got another point, B double dash 2 1, and the C double dash is what? C double dash is 0 1. So what is that? C double dash 0 1. Already said that 0 1, it is going to give us a, now you substitute here 0 1. C double dash is 0 1. 0 1 will be 2. So don't consider. So this we have discarded, this we have discarded, and this we have got it, and this is the only point 2 1. So you have got a new solution. And incidentally you find that it is 2 1 and 2 1 is an integer. 2 is an integer and 1 is an integer. So I am happy that this can be my solution. So what is that you are having? So we are getting that B dash, B double dash, it is 2 1, which can be my solution. Can you understand? So this can be my solution. So because 2 is an integer, 1 is an integer, so I will remember this. So what is that I have done here? I have created two subproblems because of the reason that 1.5 lies between 1 and 2. So x2 less than, that means what? Below 1 you will search for a integer solution. It can be 1 or below 1, no problem. Okay, and but always remember that the maximum or minimum will occur only on the vertices of a polyhedron. So you will not get anywhere inside, you will not get that. It can lie only on the vertices of a polyhedron. So you see that it can be this or this, 4 corners. So we have found that this corner is discarded, this corner is discarded, this is giving the least value. The only possibility is B double dash, which is 2 1, and for that, what is that you get now? So you will get this. So from subproblem 1, see what is your sum from subproblem 1 for, see, for subproblem 1, B dash, see what is that I'll write here, Z, see, max of Z, at which point now? B double dash of 2 1. Now that means what? 2 into 3 is 6, plus 1 into 2 is 8. So you get maximum, and x1 is equal to 2, x2 is equal to 1. They are integer solutions. So you see that you are getting an integer solution for that. So you see that this can, you keep this in your mind. So this can be your solution. That means what? Though it is giving less, you see that I told you, I gave you the reasons why it should not be corrected. I have not corrected manually. Okay, now that I have used a technique and found that a solution, that solution is, okay, the solution is integer solution, and that it is giving a maximum which is not that much far away from my 9. Because of that reason, I consider this, I keep in mind this as my solution. Are you able to understand? Now let us come to this subproblem 2. What is that subproblem 2? x2 is, now you are going to search for a solution. Second subproblem, that is subproblem 2 you are going to take. You are going to consider the region x2 is greater than or equal to 2, x2 is greater than or equal to 2, that you will find, you will search for a solution on, that means what, you will draw the line x2 is equal to 2. What is that you will do? x2 is equal to 2, draw the line x2 is equal to 2, search for a solution on x2 is equal to 2 or above the line. Are you able to catch what I am telling you? So you see that for subproblem, this is for subproblem 1, this is for subproblem 1. Now where is that, what is that you will do? So x2 is equal to 2. So x2 is equal to 2 is here. So x2 is equal to 2 is the same line I am drawing here. So this is already drawn. So x2 is equal to 2. Now you are going to search for a solution x2 is equal to 2 line or above the line. Are you able to catch what I am telling you? So you are drawing that x2 is equal to 2. It is an additional constraint. Now you are going to search for a solution on the line and above the line. Now on the line means what? This is x2 is equal to 2, and above the line means, where do you get? Your region lies only in this O, A dash. See here O, A dash, B dash, C dash and C, and beyond C dash there are no points. you do not have that region included in your feasible region. So you cannot consider any point above that. Don't consider any point above CC dash, because no point can be a solution, because your feasible region is lying below. So you will not consider. So you will consider only CC dash. So what is that you will do? So you draw this line, and incidentally what is that you find? This is the set. That means what? Here you draw the line x2 is equal to this thing. No points are above that. No points above that. So your region is the line itself. This logic you are able to understand or not? So you see that, see, you are drawing x2 is equal to 2 line and it is CC dash. Now you are going to consider the region and on the line and above the line. But since no, the region is not above the line, your region is the CC dash line itself. Region is what? Region is CC dash. So your CC dash itself is your region. That itself is a region which contains points. So we are totally confirmed that either your 0, 2 must be a solution or 3 by 2, 2 must be a solution. Are you clear with this? That means your either this C 0, 2 must give you a solution, or C dash 3 by 2, 2 must give a maximum solution. This 0, 2 I will not take, because already we have discussed this point and we found that it is giving less and it was discarded, though it is an integer solution. Though it was an integer solution, I discarded it because I know I want a better solution than that. I want a, because it was not giving me the maximum. So if you get it, this is another point I want to insist, that if you get a fractional value and your maximum is more, that is your maximum is comparatively more, and even though you may have some integer solution, you have to consider this fractional value, because you have to divide them into sub problems and go through them and try to find out the integer solution. So if you get an integer solution to that, does not mean that that is your maximum, because fractional value solutions, that is for the decision variables, may give you a higher value, in which case you have to go for the process. That means what? That process, that means branch and bone process must be there, and you do that and get. Now you see that the 0, 2 may be an integer solution, but it is not giving me the maximum. Now you see that 0, 2 giving me a solution, it was giving me 4, but I could find another integer solution which is giving me 8. So which one will I choose? I will choose only this. So you see that this was discarded. Now coming to this C dash 3 by 2. Now what is that you must consider? Now consider this C dash 3 by 2, 2. Now 3, it was giving a solution. C dash, so what was it giving you? Now you see that, now I will consider this. So I will consider this. CC dash itself is my solution region. CC dash C 0 to C dash, what is that? 3 by 2, 2. And this is my solution. So for this solution, what is that maximum? Max is equal to max of is that, see 3 by 2, it is nothing but what? 3 by 2, it is 9, it is 8.5. So it was giving 8.5. So you see that this is a better solution. So I will go for correcting this 3 by 2. That means try to get an integer solution. Now you see that when you are doing this, see when you are going to, now what I mean is that, now what does it mean? Your x1, this is your x1 is equal to 3 by 2, and this 3 by 2 means what? 1.5. So 1 less than or equal to 1 less than here 1.5, 1.5 less than 2. Now that means what does it mean? You will, your x1 value, you are going to create 2 subproblems. Here again what? Already 2 subproblems have been created, and through this I am going to create 2 other problems. What is that? Already 2 subproblems have been created, and using this I will create 2 other subproblems. And what are the 2 subproblems here? See, subproblem 3 I will write. Subproblem 3. What is that subproblem 3? Oh, it is original problem. It was original problem, and then what is that you are having? This original problem, and then here what is that you get? Here your original problem, and you had what? x2 less than or equal to 1. See, because this x2 less than or equal to 1 less than 2, greater than. This is my original problem, and because of this x2 greater than or equal to 2 only, I could identify my C and C dash as the region. That C and C dash has been found to be the region of my solution, integer solution, because of the additional constraint x2 is greater than or equal to 2. Are you able to catch? Now that your region is, where is your region? This is not OA dash, these things are not your region. For this problem, sub-problem 3, your CC dash is the only region. Are you clear? So where is the region? The region is nothing but your CC dash, nowhere, it's a line. Because you see that x2 is greater than or equal to 2 means it is either on the line or above the line. Since there is no region existing above the line, your region is CC dash. Now that is the reason. Here, if you are going to create sub-problems out of this, you must search for an integer solution only in CC dash. Are you able to understand? So this is the biggest understanding that you must have. Now, additional constraint, and because of that, say I have got here. What is that you are having here? So first is x1. See, what is that? x1 is less than or equal to 1 and x1 is greater than or equal to 1. So how many sub-problems here I will create? x1 is less than or equal to 1 and sub-problem 4, which is original problem, x2 is greater than or equal to 2 and x1 is greater than or equal to 2. Are you able to understand? So you see that here, because of this, I am creating two sub-problems. The region is now CC dash. Again and again I am telling you that the region is CC dash and it is only that line is the region. And what happens is that here, because of this 3 by 2, I am creating two different problems. One is, because it is lying between 1 and 2, I will search for a solution x, because this is x1 coordinate. So x1 is less than or equal to 1 and search for an integer solution in the region x1 is greater than or equal to 2. See, here I have written here 2. Now let me go for this sub-problem 3. Now when you go for the sub-problem 3, this is your x1 is equal to 1, correct? So this is it, and x1 is equal to 1, search for a solution below that. That means what? You will search for a solution below this. Now you tell me where is your region. Now you see that this point, I will call it as C triple dash, and this is the region. Try to understand, CC dash is your region. Okay, now you are drawing the line x1 is equal to 1 and you must search for a solution on the line or below the line, and the point of intersection is your C3 dash. C3 dash. Now C3 dash is the only solution, that too nowhere else, it is on the line only. So your C3 dash, what is the coordinate? The coordinate C3 dash is here x2 is equal to 2, here x1 is equal to 1, so this is 1 2. So what is that C3 is C triple dash? So C triple dash is your x1 is equal to 1 and x2 is equal to 2. So this is your point. Now I have got, now what is that region? Region is nothing but what? Your CC dash itself. So C, either it can be C or C triple dash. What are the two solutions that are now available? One, either C or C triple dash. But C I don't want, because C is discarded. So in this you get, for this sub-problem 3, it is nothing but what? In your C triple dash, it is nothing but what? 1 2. So you get this 1 2, and what is the solution? Max of Z at 1 2. What is the 1 2 means what? It is 3, it is equal to 7. Now you see that you are getting 7. So you are getting a solution. This is an integer solution. 1 2 is an integer solution. And what is the solution that you have got? Maximum 7. Now already have got an integer solution which has given me 8. So why should I take this solution? So forget about this solution. So we say, mathematical term, we say that this is fathomed. Fathomed means it is as good as given up. So this is fathomed. Fathomed. Fathom means this is compared to this. I have got here for some integer solution. I have got here the maximum, and this is giving me less. So why should I take that? Better give it up. That is the meaning of that. So it is fathomed. Now, another subproblem 4 is remaining for us to solve. There is a chance that may give me a better solution. So why not I try that? So what I am going to do is, so for this I have decided. Now come to this. What is your x1 is equal to 2? Now you see that you draw this line. Already this is drawn, x1 is equal to 2. Now, by the by, you must, again and again I am telling you that your region, where is your region? Your region, after coming to this subproblem and subproblem 4, subproblem 3 and subproblem 4 are considered with respect to the region CC dash, which is a line only. CC dash, nowhere else. It is lying between C and C dash. Are you clear this? So you see that it is lying, and above that or left or right, nowhere you will get solution. So CC dash is the line, it is the region. In that place only you will have your solutions. If you are going to create problems with keeping this, then you can search for a solution in CC dash and nowhere else. Nowhere else, absolutely not. You cannot do that. Now keep this in your mind. Now listen what I do. See, here you see that I draw this line. X2 is equal to what is that? X1 is greater than or equal to 2. That means I draw the line x1 is equal to 2, and this is my x1 is equal to 2 line, and search for a solution on the right hand side. But you see that you're going to search for a solution which is not in my region, because your region is CC dash. Are you able to catch what I'm telling you? So CC dash is my line region where I can search for a solution. But if you consider this subproblem 4, it asks me to find, that problem asks me to find for a solution beyond this x1 is equal to 2 line. That means what? There's all the solutions, nowhere they lie in my CC dash line. That means what? It is not lying in that region of solution where I am considering. Therefore, this problem is cannot be considered, because this is not going to take me to the problem itself. That means what? It is also fathomed. It is fathomed for the reason that it is not lying in the, that is, it is not lying in the region of my solution. That means CC dash is the region of my solution, but this particular subproblem 4 asks me to find solution where it is where the points will not lie in CC dash. Therefore, it is fathomed. That is not considered. So the problem, now you cannot do anything other than this. The problem is over, because only we have got the that is only subproblem. 4 subproblems we could get. In this particular problem, we could create only 4 subproblems, and the subproblems come because of the fractional values that we get. But no fractional values anywhere we get, therefore the problem ends here. That means we need not proceed further on this. There is nothing to worry on this. Okay, now you see that we have got solutions on all these things, and finally what happens is that you have got solutions like this. 2 solutions we could consider. Solution 1, because of subproblem 1 we could get 8 and the integer solution. Subproblem 3 we could get integer and you get this solution. Already here also integer solution, here also integer solution we got, but all those integer solutions were very less, and therefore we discard among all the integer solution. This is the best, and therefore this is my solution. So my solutions to the problem is what? This is my solution to the problem, and the all others are either we call them as discarded or fathomed. And this is how we use. And you know what is the meaning of branch and bound? When you get fractional values for the coordinates, we branch out, we create sub problems, we branch out and what, try to find out using and try to find out the integer solution. That is, we use that process. That is, if it is like this, x1 is equal to 3 by 2 means what? It is 1.5. So look for a solution below 1.5 and look for a solution above 2. In that way we branch them, and you see that, and we always keep a bound. What is that upper bound? You see that here you have got 8. We have got for all integer solution, we found lot of integer solutions. We found, say for example, you had integer solution, but after using the branching method, I found at one place the a solution for the sub problem to be 8. That means what? I will keep this as my bound. That means what? If for maximization, this is my bound. If it is a minimization, it should be less. But in this particular case, this is my bound. In the sense, this problem is giving me the maximum value for an integral values. The maximum for an integral solution. That means what? This is called integral solution. x1 is equal to 2 and x2 is equal to 1. That is an integral solution. That is integer values. For these integer values, my 8 is the maximum, and I will keep this as my bound. Go on finding the other solutions. Go on finding the other solutions using the branching. And when I do that, that is creating sub problems. Wherever it is required, I go for I create sub problems. For each sub problems, I try to find out integer solutions, keeping this as my upper bound. And here I compare. I always compare. And if any solution is, if all the solutions keep less than this 8, I fathom all those solutions. By chance, I get somewhere a solution which is more than this 8, and the solution is also integer solution, that this is dropped and that is kept as my upper bound. So that is why we call it branch and bound method. Okay, now so you see that this 8 is kept as my upper bound, and we got the solution here 7. But 7 is less than 8, so I need not consider. This is my upper bound, so 7 is discarded. So like that, we go on finding, we branch and fix a bound, and then finally arrive at we try to find a solution which will give us the maximum. At the same time, the integer, the x1, x2 values of integers. So this is your branch and bound method, and we don't stop with this. What we do is, you call this as your original problem, because there is no space for me to write on the board. So I will just write this as, see, so I'll rub off all this. See, I'll rub off all this. The flow chart I'll write the flow chart. So what is my flow chart is like this. It is your optimal, see, original problem. What was the optimal solution that you had? You had the optimal solution as, see, it is a max of z at I think 3 by 2, 2 by 2 and 2 by 3, 6, 3 by 2, 3 by 2, 2, 3 by 2, it is 6 and 3, 9. Okay, so we had like this. So we had max of z at 2, 3 by 2 is equal to 9. So this is my problem, see. So this was my problem, and 2 and 3 by 2 was my solution. But this 3 by 2 was not an integer, so I split it into 2 sub problems. So this I'll write here. So I had x2 is less than or equal to 1, and because of that, what is that you had? Because of that sub problem, see, this is sub problem 1, and for sub problem 1 we had like this original problem x2 is less than or equal to 1, and we had the solution as what? 2 1, x1 is equal to 2, x2 is equal to 1, max of z is equal to 8, and this is your x2 is greater than or equal to 2. Here for this you had original problem, x2 greater than or equal to 2, and it is 3 by 2. So max of z is equal to 3 by 2 means 4.5, 8.5. Here you see that this is a fraction, so we split it into two problems. And here it is what? It is x2 is less than or see x1. See here it is x1 is less than or equal to 1. So this is your problem. x2, see original problem, then x2 is greater than or equal to 2, and x1 is less than or equal to 1, max of z. So what is that you are having? x2 is, so these are the constraints that we have got. So you could get what? So you could get 1 2. So maximum of z is equal to what? It is equal to 7. For x1 is equal to 1, x2 is equal to, so this is an integer solution. Coming to this, it is original problem, x2 is greater than or equal to 2, x1 is greater than or equal to 1, then this is what? No feasible solution. I gave you the reason, because it is lying on the region where your solution set is not there. So this is discarded. So this is your flow chart. So this is what you have. So you see that this one you keep here, what is that you are having here? See, this is 8.5, this is, see, this is fraction, so this cannot be treated, and you see that this is non-feasible, so this is fathomed, and you see that this is my upper bound. So this is upper bound, and I got another solution like this, but this solution is smaller than this, so this is also fathomed. So this is fathomed, because this is a fraction, I split it into this. So this is the flow chart for this, and this flow chart goes on like this. You take the original problem, find a solution. If it is a fraction, split it into two problems, find the solution. If you come across again any fractional values, split them into sub problems, and you see that this is your sub problem 2, and you split it into sub problem 3, sub problem 4. So you see that we split them into sub problems like this, and so this is how it is done, and final solution is that, so solution is max of z is equal to max of z for what? Here 2 1, that is equal to 6 plus 2, that is equal to. That's all. So this is all the problem, and you have to do only like this. If you use the simplex method, it will be very difficult, and the process will be very cumbersome, difficult, confusing, and it will frustrate you. So this graphical method will be comparatively easy, provided you are very carefully doing. So let us see more and more in all other branches of mathematics in the coming days. Thank you.